Hi everyone. How would you graph the following piecewise function? Graph y equals f of x if f of x equals x plus 3 if x is not equal to 3, but f of x equals 7 if x equals 3. I'll give you 20 seconds to ponder this. Okay, the domain is all real numbers. How do you graph y equals x plus 3? Well, that's just going to be a slanted line, slope 1, with y-intercept at 0, 3. You should know that from section 0.14. But wait a minute. For now, as we graph the first piece, we're not allowed to have a point with x-coordinate 3 because 3 is not in a subdomain for this rule. So for now, we have to put a hole at x equals 3. Now on the line, the hole is at 3, 6. If you were to just graph y equals x plus 3, there's normally a point on the graph at 3, 6. But because we're excluding x equals 3, we're not allowed to have a point at 3, 6 on the graph. We have a hole for now. Now, wait a minute. What does the second rule do? Y equals 7 if x equals 3. In other words, the point 3, 7 is on the graph. 3, 7 is on the graph. That's like a moon. The graph looks like, well, let's reiterate. We graph the line y equals x plus 3, except we leave a hole at the point 3, 6, since 3 was deleted from the subdomain. The bottom rule defines f of 3 to be 7. That's what it basically says. F of 3 equals 7. That's what the bottom rule says. That's why 3, 7 is on the graph, which means the graph of the piecewise function looks like that. I hope you're able to give yourself an A+. So in calculus, we say that there is a removable discontinuity at x equals 3, in the sense that you can get a continuous function if you just take this moon point and move it down and fill in that hole, spackle in that hole, if you redefine f of 3 to be 6. A removable discontinuity is a fancy way of saying hole. That's what you call a hole in calculus. We have a removable discontinuity at x equals 3. The point 3, 6 is a hole. There are points to the left on the graph, points to the right on the graph, but it itself is not on the graph. In fact, we would have a hole there whether the point 3, 7 were there or not. Now, I don't really like the term removable discontinuity because you're not allowed to redefine f of 3 just because you feel like it. There's no rule by which we're allowed to move this point down into that hole and spackle in that hole. So I don't think the term removable discontinuity is appropriate. I think it's a misnomer, but in calculus, you use it. It's a standard term in calculus. We have a removable discontinuity at x equals 3. There's a hole at 3, 6, whether there's a point at 3, 7 or not. But there is a moon up there. Notice the graph does pass the VLT. We have a function here. Now, we just said that f of 3 was 7. The function value at 3, the y-coordinate at x equals 3, was y equals 7. That's why the point 3, 7 is on the graph. So f of 3 equals 7. That's a pre-calculus question. What is f of 3? What's the function value at 3? It is 7. But wait, doesn't 6 have some relevance though? Yeah, but that's a calculus idea. That's a limit. So in pre-calculus, we say that f of 3 equals 7. But in calculus, we can say that the limit of f of x as x approaches 3 is 6. In other words, as x approaches 3, f of x, the function value, the y-coordinate, approaches 6. It's like Romeo and Juliet. Romeo is running along this graph from the left, approaching x equals 3 from the left. Juliet approaches x equals 3 from the right. They're both approaching the point 3, 6. So the limit value is 6. whether or not they meet or not. So we're not being very romantic. We don't care if they meet or not. What matters is that they're approaching each other. So the limit of the function as x approaches 3 is 6, even though the 0.36 itself is not on the graph, the 0.37 is. So once again, and make sure you understand this distinction in calculus, the function value at 3 is 7, but the limit value as x approaches 3 is 6. The function value is 7 because 3, 7 is the point on the graph, but the limit value is 6 because Romeo and Juliet are approaching y equals 6, even though they never meet. Aw. Next, we're going to talk about a graph that kind of looks piecewise, but it has its own applications next time.